In this video, we're using linear equations to solve word problems about simple interest. We'll cover problems like this with solutions like this. So stick around for a bunch of information about how to do these problems, and then a few examples to show how we apply those strategies. In this video, we'll be looking at applications of linear equations, and we'll be focusing on applications around simple interest, which is basically just a percent calculation. Before we get into our problems, let's cover a little bit of background information. Frequently, when we look at textbooks or other math resources about simple interest, we see this formula, I equals P times R times T. But we really shouldn't look at this as some special fancy formula because it's just a percent calculation, and then that amount might be applied over several years or several months or some longer amount of time than just one-time percent calculation. So for our first example, let's say $800 is invested for 1 year at 3% simple interest. What is the amount of the interest, and then what is the value of the investment after 1 year? We'll start off by using this formula, and we'll substitute in our values for P and R and T. P is the principal, the initial amount of the investment, or loan. In this case, it's an investment. So P will equal $800. R is the interest rate, but we want to write that as a decimal number. So our 3% interest rate would be written as 0.03. We can find that by doing 3 divided by 100 because percent means out of 100. It's important that we don't use the percent in this formula, or really in any percent calculation. We always like to change that percent into a decimal number, or at least out of a percent form. So you could use the fraction 3 out of 100 to represent 3%, or you could divide 3 divided by 100 to get that decimal number 0.03. Either of those would be the number that we would want to substitute in place of R, but definitely not just the number 3. Finally, we have this variable t for time. The problem is not very clear about that 3% interest rate, so we will assume when we see an interest rate that it applies for 1 full year. So the time is 1 year that passes, 1 year at 3% simple interest. So t equals 1. Now let's substitute those values into the formula. And in this formula, we have only multiplication, 3 numbers all multiplied together. So let's start with 800 times 0.03. And we can remember that this is exactly what we would do if we just wanted to find what is 3% of 800. Change the 3% to a decimal, multiply by 800. So the first part, doing the P times the R, just is calculating the percent. How much is 3% of 800? It gives us a result of $24. That would be the amount of interest after 1 year. Well, after each year. But in this case, we're only interested in 1 year of the investment. So $24 just one time. T equals 1 because only 1 year for this investment. So that $24 per year is equal to the amount of interest for this 1 year. So we have the first answer, the amount of the interest is $24. We found 3% of 800 and multiplied that by the number of years of the investment, which in this case was just 1 year. There's the follow-up question, what is the value of the investment after 1 year? So remember that we initially had this principal of $800, and now we are about to gain $24 of interest. Adding that into the original 800 gives us our total value of this investment after 1 year of $824. The original $800 investment plus the $24 that was gained through the interest for that year. So circling back to this formula, we absolutely can be substituting our values in when we find them, but let's not get disconnected from the fact that this formula is just calculating a percent and then multiplying that percent by how many years the investment takes, because the interest that we calculate would be the interest for each year. And that's just doing P times R, our usual percent calculation. an amount times the percent after we change it to a decimal or a fraction. So here's an example for you to try. $4,800 is invested for 1 year at 5% simple interest. What's the amount of that interest, and what would be the total value of the investment with that interest added in? Pause the video to try it out, and then restart, and we'll look at the answer together. So my first calculation was just to find what is 5% of $4,800. So I multiply $4,800 times 0.05, 5% after we change it to a decimal. And that equals $240 of interest. And we notice that this problem is only asking about for 1 year, and that's exactly what that calculation gives us, the interest for 1 year. So that's our amount of the interest, $240, and we will add that into our original principal of $4,800 to get the final total value of this investment after 1 year, $5,040. I didn't use that simple interest formula, so let's just take a quick look at that also. But remember that it's connected to just finding a standard percent calculation. We have some original amount, the principal, and we multiply it by a percent that we change to a decimal. And then we would multiply that by how many years if it was repeating. But so far we've only seen problems where it's just for 1 year, so we're multiplying by 1. I've written it out like this, where I substituted in place of P, R, and T, the principal, 4,800, times the rate as a decimal, 0.05, times T for time, the number of years, just 1 year. And we get the same result, $240. And notice that in both of these calculations, we've only calculated the actual amount of interest, the amount of extra money that goes back into the investment. So to answer the follow-up question, in either case, we need to take the number that we calculated for interest and then add that back into our original principal, the original amount of the investment. Now we have one more example to cover before we get into our full problems. We want to see how can we use these calculations or this formula when we have an unknown quantity, either our principal or our rate or our time could actually be an unknown. And in that case, we'll need to use a variable, and that will help lead us to a much broader range of equations and problems that we can solve once we start using variables to represent unknown amounts, and then still press on with all the calculations that we would ordinarily do, like multiplication if we're finding a percent of a number. So let's check out that next example. We're looking at this situation where X dollars, an unknown amount of money, we're representing that by the variable X. X dollars are invested for 1 year at 2.6% simple interest. How much is the interest, and what is the total value of the investment? And we have an unknown quantity. We're going to assign that variable X to represent the principal for this investment. And we're going to try to do all of our calculations exactly as we did them before. The big difference is that we're not going to be able to calculate like actual numbers. We're going to have expressions that are in terms of that unknown variable. But keep in mind that we're trying to do and show the exact same calculations that we were doing when we actually had all the numbers to work with. So we've been doing things like taking the principal amount and multiplying it by our interest rate once we change that to a decimal number. So let's take the 2.6% because now I've added a tenths place to our decimal number just to keep things advancing. But just remember that when we have a percent that we can divide that by 100 to change that to a decimal number. And yes, that's the same thing as moving that decimal point 2 places, but I do like to connect that back to the reason that we move it 2 places is because we're dividing by 10 and dividing by 10 again, which means dividing by 100. 10 once, divide by 10 again means divide by 100, and each of those divide by 10s is move that decimal point. So yes, by all means, just think move that decimal point as long as we're being accurate with it. But know that that's because a percent means out of 100 or divided by 100. So first piece of business here was that we've decided that our interest rate written as a decimal would be 0.026 to represent 2.6%. Now we would want to take that percent as a decimal and multiply it by the principal. But our principal is a variable instead of an actual number. But that won't really change what we want to do going forward. We're going to take that principal, x, and we would multiply that by the percent as a decimal, 0.026. And we can't get an actual number calculation out of that. We would just say, well, that's this variable expression, 0.026x, which means 0.026 times x. And as soon as we know what that principal is, we could put that number in place of x. But if we don't have that number for the principal, we're just going to have to press on with using the variable x in place of that number. So that is our amount of interest. It depends on the principal, which is unknown. For that follow-up question, what is the total value of the investment? Again, we want to remember what we did in the problems where we actually had that information, where we had the actual numbers. Once we calculated the amount of the interest, we would want to add that back into our original principal, the original amount of the investment. And that was, in this case, it's x. It's still unknown. But we would say take that original investment, the principal x, add to that our interest, which is this expression, 0.026x. And those two things added together would be the total value of the investment, our original principal with this interest added in. And we can do a little bit of algebraic simplification. We can't get to an actual number yet. Still, we can't get to a number about what that original principal was, but we can simplify this expression because that's going to be a necessary part of us solving these equations that we are about to see, I promise. So we think about combining like terms because both of these terms have the variable x, and the x doesn't have any exponents. And when we see that we have like terms, we want to combine these coefficients, add the coefficients. We want to add this positive 0.026 to the coefficient right here with x. And when it's just the variable x, it works exactly like saying 1x. You could say, well, 1 times x, any number times 1 doesn't change its value. So calling x 1x is fine. We haven't changed, we haven't made a 6 into a 9 or anything like that. It's the same number. And having that number there helps us see how to add these numbers up. Sometimes it could be helpful for us to remember that when we are adding numbers with decimal places, we have to kind of think about lining those decimal points up. So it's like a 1 whole plus this tiny piece, 0.026. And when we add them together, we will get 1.026. That will be the coefficient of this simplified expression, 1.026 times x. So our terms were 1 whole x, 1 whole principal. Then we've got the interest calculated, just 0.026 of that principal, but we can still combine those like terms and say that now we have 1.026 of our principal. We have the entire original principal plus the extra 0.026 times x, because that was the extra interest part. Add it all up, we get 1.026 times x. So we're going to take this idea into the next few problems where we have to begin to work a lot more with variables to solve these problems. So if necessary, take a moment to kind of look back on this, maybe replay what I just talked about so that we're feeling more comfortable about this algebra part that we're doing at the end where we're saying like, oh, an x plus a 0.026x, we can do that and we can get a 1.026x, and that we have to kind of do that because that original principal was unknown. But we still do all the same math steps, like multiply that principal times the rate, written as a decimal, and then add that interest back into the original principal x. And when we have unknowns, it's going to have to play out this way. But we're going to right away look at some actual problems where we can see the benefit of using the algebra like this when we have some unknown quantities. Let's tackle one more background problem about investing into two separate accounts. We're going to use the same steps that we did before, just individually with two separate investments. So in this problem, $2,500 is invested for 1 year at 1.5% simple interest, and $1,500 is invested in a separate account for 1 year at 1.2%. So how much is the total interest? And then what would be the total value of both investments? So it looks like we have a total of $4,000 being invested here, split up into one investment of $2,500 and a different investment of $1,500. So those two amounts added together equals that original $4,000. So for our total value of both investments, we're hopefully going to see that we get a result that's above $4,000 because that was just our original principal. So we've got an idea, a ballpark estimate of where we're going to end up, a little bit above 4,000. But let's apply these ideas that we've been using over the last few problems, but one investment at a time. So our first investment, $2,500 at 1.5%. So that percent as a decimal would be 0.015, and multiplying that to the 2,500 equals 37.5, which means $37.50. Then our second investment, $1,500. This time it's at 1.2%. So we'll change that to a decimal, and that would be 0.012 is 1.2%. And then we'll do that multiplication to calculate the amount of interest in this second account. And that result was $18. So to find the total interest, we will just need to total up, sum, add together the different interests from the two different accounts. $37.50 from the first, $18 from the second. Looks like that's going to give us a total of $55.50 for the total interest. And then for the total value of both investments, we noticed that we started with $4,000 if we combined the principal from those two accounts. And then we'll add in our interest, $55.50. And another opportunity to notice that we like to line up those decimal points when we're adding things up. $4,055.50 would be the total value of our original principal plus this extra interest, the total from the two individual accounts. Okay, now we're ready to tackle some problems. Here's our first journey. $3,000 is split up into two investments for 1 year. The first account offers 1.8% simple interest, and the second account offers 2.5% simple interest. How much is invested in each account if the total interest for 1 year is $67.30? Now, at this point, we might feel like we have no idea how to start. And that's okay, because there are some specific strategies that we have to apply to problems like these. And the more problems that we do like these, we get a better feel for how these strategies come together. So I don't expect that it's going to be obvious right now how we should do these things. So the first thing that we need to do is to notice, what is it that we're trying to answer here? What are we trying to figure out to solve this problem? We need to know how much is invested in each account. So we need to know the principal for each of these two separate accounts. And we know what the total interest would be. It would be $67.30. So we'll go slowly, but we're going to try to connect back to a lot of the ideas that we've just surfaced over the last few examples and foundational information. Since the amount in each account is unknown, that's where we're going to use our variables. And at this point, we also would like to incorporate the strategy of how we can represent two unknowns using only one variable. It makes this problem a little bit more concise for us to solve. So there are two unknowns, the principal in each of these two accounts, but we know that the two principal amounts would total $3,000. So this is an instance where we have two unknowns, but we know that when they're put together, the total would be $3,000. And the strategy that we use for assigning variables in this case is that we would make one variable just be X or Y or whatever symbol or letter we would like to use. So let's say X will equal the principal in the first account, the 1.8% account. And then the amount into the second account would be this total with X subtracted away, because our total $3,000 is being split up into two separate accounts. If X goes over here, then from our original $3,000, we just took X out to put it over here. We subtracted away X. That means we have $3,000 minus X left over for our other account. And no, we still don't know what X equals, but whatever X does end up equaling, we would find the other amount by doing 3,000 minus X. If X was 1,000, then the other account would mean 3,000 minus 1,000 is 2,000. So I've got another video where we talk about that strategy about when we have two unknowns, but we know the total. And that's exactly what we're applying in this case. So total minus the unknown, 3,000 minus X, would be the principal for the other account, the 2.5% account. Next, let's look back at this problem to try to figure out our path forward. We've got the principal represented by these variable expressions, X and 3,000 minus X. We now also need to incorporate that this first account calculates interest using 1.8% rate. The second one uses a 2.5% rate. And the total interest would be $67.30. Now, we just had an example where we looked at having two separate accounts, and we could find a total amount of interest by doing principal times interest rate for one, principal times interest rate for the other, and once we get those two amounts of interest, we add them together. And so we want to try to do that with this problem, even while we still have these unknown amounts and these variable expressions. So remember, when we did the interest calculation, we would do the principal times interest rate. So let's start to write that out and see what it looks like. So I've started off with 0.018x. Where does that come from? That is our interest calculation from this first account, where our principal was represented by the variable X. It was a 1.8% interest rate, so as a decimal, that would be 0.018. And our interest amount is the multiplication, 0.018 times X. So that first term right there represents the amount of interest from the first account. The best way we can do it while we still don't know what that principal is to do this and say, well, whatever that principal was, you do it times 0.018, and that's how you get the interest. And so now let's use that idea with the second account. The second account, our principal is a little more complex. It's this expression 3,000 minus X. The interest rate is 2.5%, so that would be 0.025. So let's write 0.025 multiplied by our principal, 3,000 minus X. So there's the interest calculation for that second account. The rate as a decimal, 0.025, times the principal, which we have represented with 3,000 minus X. Now we know that the total interest is $67.30. So that means we can finish this equation by saying the interest from the first account added to the interest from the second account would equal our total interest of $67.30. So there is the equation that we will be solving. We'll pause for a second to digest kind of reflect on what we just saw about setting this thing up, where we had to notice that we have two unknowns, but we knew what the total was. That gives us a specific strategy for setting up those variable expressions to represent the unknowns. After that, we went right back to our usual calculations. The interest is principal times interest rate. Interest from the first one added to interest from the second one needs to equal that total interest that they tell us, $67.30. So let's rewrite this equation on a new page so that we can go through all the steps for solving it. But then we'll come back here because this is really home base where we've defined these variables. X is the principal in the 1.8% account. 3,000 minus X is the principal in the 2.5% account. We want to come right back to where we define those variables to really give the best kind of answer to this question. Now we're ready to solve this equation, and usually we do this by, at first, looking at the two sides of this equation separately. The sides are separated by that equals sign. Let's just do a little hash line down the middle so that we're thinking these two sides equal each other. All this unknown stuff on the left side equals 67.3 on the right side, $67.30. But let's start just looking at this side where we have all the algebra and look for the ways that we can do some simplifying, because we ought to be able to get this down to just one variable term and one number term. Usually it might look a little bit different, but that's really our goal to get these linear equations solved. So we need to notice that we've got this instance up here where we need to distribute. We're multiplying 0.025 times these two terms, 3,000 and minus X. So we need to distribute with multiplication 0.025 times 3,000. That equals 75. And then 0.025 times minus X. So the only thing we can do is just make that 0.025 as the coefficient, or think we're multiplying it by -1 for that -1x. So minus 0.025x. And that's what we've got after we've done the distributing for that expression right up there. Let's just recopy these other terms, 0.018x. That's a positive 75, so we'll get that plus in there. And let's rewrite the right side, 67.3. Next, after that distribute, we usually are able to find some like terms to combine. And we see that we have two terms that have the variable x. One has a coefficient of positive 0.018. The other has a negative coefficient. So when we're combining these terms, we'll be adding this positive 0.018 to that negative 0.025x. And that will give us a negative 0.007x. Then let's bring down the plus 75. And the right side equals 67.30. Okay, we've done all the simplifying that we can here on the left side. We're down to just one variable term and one constant term. Nothing else can be simplified. They're not like terms. So here's where we begin to think about isolating the variable, that variable x right there. And we think that we have to do the opposite of order of operations. We're really trying to use opposite operations to undo the math that we see. And when we are undoing operations, we do this reverse order of operations. So we've got to think about this plus the adds and subtracts that are clogging up this side with the variable, like that plus 75 will take away 75. And of course, we have to do that on both sides of this equation to keep it balanced, to keep it valid, and so that we're not just changing numbers around. But the plus 75 and the minus 75 equals 0. So on the left side, we are really only left with this negative 0.007x. On the right side, we can actually do the subtraction with these numbers. 67.3 minus 75 looks like that will give us a negative 7.7. Okay, we have one more step to finish isolating the variable. We see that the x is involved in a multiplication with negative 0.007. So our opposite operation will be that we need to do the opposite of multiply and divide negative 0.007. And we'll do that on the right side of the equation also. So the negative 0.007 divided by negative 0.007 equals 1. So we're left with like 1x. And 1x is just x. We could write the 1x if we like it. I've got no problem with that. But we'll probably more frequently at this point just see now we're left with our unknown amount x. And on the right side, we'll need to divide these numbers out. And it looks like it will equal 1,100. And I remember that these were supposed to be dollar amounts, so I'll throw that in right now. It's $1,100. But let's look back at our original problem so we can get some closure on this. But we have found, when we solve this equation, x equals 1,100. So I've come back to that original page, jotted down what we just found for our solution, x equals 1,100. And we bring it back to where we defined the variables. We said x was the amount going into the 1.8% account. So that amount, now we know, is $1,100, which went there. Now, if you remember that our total was 3,000, and we know that the first account got 1,100, maybe you're thinking, oh, well, it's got to be 1,900 that's left for the second account. And that sounds like a good way to track this problem that we're working on, but have complete faith in our algebra also. So x was 1,100. If we go to our second variable expression here for the principal of the 2.5% account, we would be doing 3,000 minus x. X was 1,100. So it absolutely does have us calculate the amount that would be left over if we did originally have $3,000. So the principal going into that second account, $1,900. And we can check. That's the great thing with these problems. The great thing is not that they have a lot of layers and have a lot of opportunities to go off path and specific strategies that we like to use. The good thing is that we can check them. So once we have our answers, that in the first account we put 1,100 and in the second account we put 1,900, we can go back up to this whole description of the problem and check to make sure that we did it accurately. So the first account got 1.8%. So if I do 1,100 times 1.8% as a decimal, that would equal 19.8 or $19.80 of interest. And then $1,900 in the second account. I'm starting to get a messy page here, but we're going to wrap it up in a second. So 1,900 times 0.025, that 2.5% changed to a decimal. Let's do that multiplication. We see that it equals 47.5, so $47.50. And then what happens when we add up those two amounts of interest? It does equal $67.30. So we for sure have got the right answers. $1,100 in that first account, $1,900 in that second account. Now let's try our next example. Jay invests 3 times as much money in an account earning 3.2% as they have in a 2.1% account. How much total money was invested if the total interest earned after 1 year was $81.90? So we're looking for the total money invested, but it also looks like we don't have exact figures for the amounts invested in each account. The information that we have is that 3 times as much is going into the first account as is going in the second account. So we'll need to use some variables to represent those unknown quantities, and we are hoping to use only one variable to represent both unknowns. We will be able to do that because of this information that there's 3 times as much money in the first account as there is in the second account. So it's not like our previous example where we knew the total being split up. This time we have a different kind of information where we know that this amount is 3 times as much as this amount. So let's see how we can represent those two amounts with variables. So we have an amount going into the 3.2% account. We have an amount going into the 2.1% account. And we don't need to use two variables because we know that the amount in the first account is 3 times as much as the amount in the second account. So we can say, let's make X be the amount in that second account, X, and the first account has 3 times that amount. So 3 times X. And that's how we'll use the variables for this problem. And again, this comes back to investing 3 times as much in the first account as they have in the other account. So the other account can be X. That first account can be 3 times X, 3 times as much money. Now let's try to build the equation using those calculations we've been doing to calculate the amount of interest, the principal times the interest rate as a decimal. So in our first account, the principal in there is 3x. The interest rate is 3.2%. So as a decimal, 0.032. There's the amount of interest from the first account. In the second account, our principal is only x, and the interest rate 2.1%, so 0.021. There's the amount of interest from the second account. And we know the total interest is $81.90. So when we add up the interest from the first plus the interest from the second, it should equal 81.9. Now let's work to solve this equation. We're looking at the left side of this equation to see what we can simplify. We have 3x times 0.032. And notice that we don't have two separate terms with an add or a subtract, so we're not going to distribute. We just have 3 times x times 0.032. So we'll multiply the 3 times the 0.032, and then multiply that by x. That gives us 0.096 times x. Then we'll go over to the next interest calculation, which is just 0.021 times x, so 0.021x. And let's copy down the right side. It equals 81.9. Now we can see that we've got some like terms that we can combine. These two terms that are left here both have the variable x, so we'll add those coefficients together. That gives us 0.117x, which equals 81.90. And then finally, we'll isolate the variable with the opposite operation. We have a multiply by 0.117, so we want to divide by 0.117, both sides, of course. And that gives us x equals 700. So now that we have the solution to our equation, let's go back to our variables where we can see the amount in the 2.1% account was x, so that amount was $700. And the amount in the other account was 3 times x, so 3 times $700, which would be $2,100. And like before, we can check our answer. We can just grab those two results and bring them back into the problem and do 2,100 times 3.2% and add that to 700 times 2.1%. And we will see that our total interest does total $81.90. So that problem is complete. Let's tackle one more example. D invests some money in an account earning 2.9%, and $1,000 more than that went into a 3.2% account. How much money was invested in each account if the total interest earned after 1 year was $83.85. So let's start off by what is it that we're trying to find? We're trying to find the amount invested in each account. So those amounts are unknown. We'll need to use some variables to represent those unknown amounts. As usual, we're not trying to use two separate variables. We're trying to represent these two unknowns with only one variable. And we can do that because in this problem we see that some money goes into the first account and $1,000 more than that went into the second account. So we'll use X to represent the amount going into the 2.9% account. And the other account got $1,000 more than that. So we could use X plus 1,000 to represent the amount that's going into the other account at 3.2%. Now let's build that equation where we're making the calculations for interest, the principal times the interest rate as a decimal. So in the first account, we have X for the principal with an interest rate of 0.029. That's the 2.9%. In the second account, we are investing X plus 1,000. That's the $1,000 more than the first account. And that one has an interest rate of 0.032 for the 3.2%. And when we add up those amounts of interest, we know the total interest, it should equal $83.85. Now let's solve this equation. On the left side, with this first account, we have just X times 0.029. So there's really nothing there for us to simplify. We have 0.029X. I'll just put that leading 0 to keep things looking clear, and I can see that decimal point. But over here, we have to distribute. We have these two terms, X plus 100, X and 1,000, X plus 1,000. Those are two separate terms being added together. That's getting multiplied by 0.032. So it's distribute. We maybe more frequently see the multiply number in front. Here we see it behind, but it's the same operation that we have to do. We're saying these two things, in parentheses, get multiplied by this number, so that number needs to be distributed to each of those terms, 0.032 times X and 0.032 times 1,000. So that gives us plus 0.032X, and then 0.032 times 1,000 is a positive 32. On the right side, that equals 83.85. Now, after distributing, we like to look for like terms that we could combine, and I think we see some. These two terms have the X variable, so we'll add up those coefficients, 0.029 plus 0.032. That's going to equal 0.061X, and then plus 32 equals 83.85. We want to keep trying to isolate that variable X, so we need to do an opposite operation on that plus 32 and subtract 32 both sides. That leads us to 0.061X equals 51.85. We've got one more step to do to finish isolating that variable. There's that multiply by 0.061. We want to do the opposite, divide by 0.061. So let's go to a clean page where we can recopy this equation and finish solving it. Let's finish solving this equation. Divide by 0.061 as the opposite of multiply by 0.061. We'll do that to both sides of this equation. And that leaves us with X equals $850. So let's bring that solution back to our variable representations and close this problem out now that we know X equals 850. So X equals 850, and X was the amount in the 2.9% account. So now we know that amount was $850. In the second account, it was X plus 1,000 because we had $1,000 more going into this second account. So we're looking at 850 plus 1,000. So the amount in that second account at 3.2% is $1,850. So there we have the amounts invested into those two accounts. To recap these problems, the equations were all built in pretty similar ways, where we had the principal times the interest rate from one account, and then we added it to the principal times the interest rate from another account, because that was a way for us to total up the amount of interest from each account. But we saw some variety in terms of how we had to use variables. We had one example where there was a known total amount that got split into two accounts. Our second problem was one where we said this account got 3 times as much money as a different account. So that was sort of a different strategy for using variables. And this one is maybe kind of similar to that second one, based on just operations that are described, where they said the first one is something, the second one is that thing plus 1,000. They said $1,000 more. So that led us to use X for one unknown and X plus 1,000 for the other unknown. But that these problems really boiled down to us doing percent calculations, the principal times the interest rate, and that we can answer a lot of different questions even when we don't know the actual principal. When we can use a variable, there are still many mathematical steps that we can do to solve these problems and answer the questions.